So the Mandelbrot set was not discovered very long ago. And there's been a lot of cool pictures of it since then, a lot of images generated by computers especially. There's also one image that I know of that was generated by 11th graders that we'll take a look at. Many of them are generated by computers, but there's one generated by 11th graders. The Mandelbrot set's like this. Let's go like this. Start with some complex number. Call it z. I'm going to define z1 is equal to, I'm going to take that complex number, I'm going to square it, multiply it by itself, so it flips around, and then I'm going to add it to itself, so it maybe moves in some direction. Take that. That's going to be z1. z2, I'm going to take this z1 right here, and I'm going to flip it around and add it to the original z0. I'm going to continuously do that. So I'm taking the output of this one, I'm squaring it, and I'm adding my original z0 over and over and over again. Okay? Do that again. Do that again. Do that again. It turns out, this is a little calculus language, it turns out that if this thing doesn't blow up, it doesn't go off to infinity. I hate doing this right after teaching a class because I have a cool little calculator program that I was going to show you, but it's not here. But you guys can check it out yourself. It's on the back of your little program, your little sheet thing. If this number does not go up to infinity, if this number stays bounded, then Z0 is in the Mandelbrot set. Z0 is in the Mandelbrot set. So Z0 is one that doesn't blow up when I do this. Here's an example, a real easy example. The real number, z is equal to 2, negative 2 plus 0 times I. That is a number which is in the Mandelbrot set. Because we can go like this. Z0 is equal to negative 2. Z1 is equal to 4 plus negative 2, which is equal to 2. Does that make sense? Z2 is equal to 4 plus negative 2. Z3 is equal to 2. Z4 is equal to 2, and so on. So the real number 2 is a classic example of a number which is in the Mandelbrot set. It's a number which is in the Mandelbrot set. Does that make sense? It's good that I don't have my calculator, because that way we have a chance of getting out of here within a reasonable length of time in a couple more minutes. So here we go again. This is exactly what I just wrote. So that thing is in the Mandelbrot set. If you take out your TI calculator, one of the cool things that the TI has is even the 84. It has a little button where if you press second, down near the bottom, it has a little eye above it. You can actually access the imaginary unit. And you might want it on your own. Check out a couple of numbers. Check out something like 0.3 plus 0.2i. See if that's in the Mandelbrot set. See what happens when I do that with it. On the back sheet of your little thing, there's a little TI-84 program. So if you have a TI-84 program and you would like to, or a TI-84 and it interests you to program them, you can actually make a program that will check any number. What it does is it actually runs 50 iterations. It goes out to Z50. If Z50 is less than 2, if the magnitude of Z50 is less than 2, then I'm just going to assume that Z is going to stay fixed. It's going to stay there. If it blows up, if it gets bigger than, if at any time it gets bigger than 2, then I'm going to assume that it's going to grow out of the Mandelbrot set. So anyway, this is an interesting enough set that a math teacher out in Sandy decided that he was going to have his calculus students do this. And they took a whole bunch of numbers and they plotted them. And what they did is they let 0 be right about here. And the numbers go up like 0.4, 0.8, all the way up to 1.2 up here, all the way down to negative 1.2 over here, up to 0.8 this way, and up to negative 2 that way. So they plotted points in the complex number plane. They plotted points. And they said, I'm going to pick a point, let's call it this point right here, which is 0.32, 0.52. They plotted that and they found that that thing didn't blow up, so they colored it black. And then these red points are points that blew up more slowly than these orange points. The orange points blew up quicker and so on. The further away you get from 0, the faster numbers go out to infinity. By blowing up, I mean their magnitudes grow towards infinity. Does that make sense? So that's how the Mandelbrot set is established. Benoit Mandelbrot in 1977, there wasn't a lot of computing power. So he worked for IBM, which helped. But there wasn't like your little iPod has more computing power than that thing than he had available to him. And so but he was able to envision this thing. Yeah, you have to.
So everything black, or is it everything on the curve?
Everything black does not blow up. If it's black, it doesn't blow up. If it's any other color, it blows up at a varying rate of speed. And you can think about this thing where each one is being squared and then summed, and then squared and then summed, and then squared and then summed. You know what I'm saying? It's kind of weird what you think what's going on, where you have these angles being added to each other, and then that offset being thrown on each other every time. It's kind of cool. Turned out that the edge of this thing is ridiculously, I can't even think of the word, more than ridiculous. You take ridiculously and you square it. It's not even enough. Complicated. Super complicated. Amazingly complicated. And I have some more refined pictures to show you in this movie that we're going to be looking at on the thing. And this movie is also interesting because it also talks about these other things that are related to the Mandelbrot set, called Julia sets. And it turns out that there's a really cool relationship between Mandelbrot sets and Julia sets. And this guy, I love him because he's super serious, awesome dude.